Bonjour. Hello, everyone. I unfortunately don't speak well enough in French to do this talk in French, but we will continue in English. Thank you all so much for being here. I am very excited to be speaking at Vox Day's Microservices Paris for the second year. So I enjoyed it so much last year, and I'm also enjoying it this year. I hope you're all having a great time. My name is Kate Stanley. I'm a developer at IBM. I'm very excited and passionate about Apache Kafka, which is what I've got down the bottom there. I recently came back from speaking at the Kafka Summit in San Francisco, which is where I got this really cool t-shirt. So if you wanted to know, that's where it's from. And I work on a product called IBM Event Streams, which is just a fully supported Apache Kafka offering with some extra value-add capabilities on top. But today I'm going to be talking about creating event-driven microservices. So first we'll do some show of hands. Who here has heard of an event-driven microservice before? Yay, lots of people. Who here's tried to build one? A few people. Anybody running event-driven microservices in production? Cool. And of those, are you using Kafka? Yeah? Have people heard of Kafka, just to check? Most of it? Okay. Cool. So hopefully everyone's here. We're here to talk about microservices, so hopefully you're starting to do this, move across from a monolith to a microservice. Martin Fowler has this lovely diagram. But what I found is actually you get really excited and you decide to move your monolith across to microservices. So you break them up, you build all these microservices, some good REST APIs. And then in practice, what happens is your user comes along and they start to make a request. And so this microservice says, well, I can't fulfill this request by myself because I just do this one thing, so I'm going to forward on to a different microservice. And maybe you've been along to some of the talks about Istio and about circuit breakers and timeouts. So going to put a timeout on your service, that's good. And maybe this one has to call this other service, that's going to also set a timeout. Maybe just one more hop here, another timeout. And by this point, a little bit of time has passed. It might be that this final microservice in the chain is quite happy and it does return the request. But by this time, the first microservice is thinking, well, this is taking quite a long time, so actually I'm going to time out and just return an error to the user. So this isn't a great situation because now your user has an error and they don't actually understand why the error has happened. To them, it's just one service still. So they have no way of knowing that actually the reason the error happened is because something timed out as opposed to something not actually working at all. And maybe I'm over-exaggerating. Maybe your microservices aren't chained that badly. Maybe it's just a little bit like this. But having latency in your system is not something that you're going to want, and really, it's not something that you can avoid if you're going to have all these REST APIs, because ultimately you just can't trust the network in a distributed system. But I don't think that latency is the only reason that you should be moving to having events at the center of your system. I think what you actually need to be looking at as well is what are you basing everything around? Are you going to be data-centric or are you going to be event-centric? And I think that event-centric really is the way to go. And to demonstrate this, I'm going to use a little bit of an example. So let's look at my current mode of transport. So if we assume that the left-hand side here is data-driven, so we're looking in a database to find out what mode of transport am I using. So I'm using an example here of how I got to Paris yesterday. So if you asked yesterday morning, I would have been in a car driving to the station. Then later on, I would have been in a train, then on the metro, and then I walked to my hotel. So in our data-centric system, we have this data. We can ask where I am. Currently, clearly, I'm on foot. But what if we move to being event-based in this scenario? So instead of saying my current mode of transport is this state, let's look at what the stream of events would look like. So an event would be structured something like my current mode of transport changed from something to something else. So first of all, it would have been changed to on foot to in a car, so I walked out of my house, got in the car, then from car to a train, train to the metro, and then metro to on foot. So there's a lot more information on the right-hand side that you're having to store than on the left, but we can actually gain a lot more insights from what's on the right to what's on the left. So it might be that your original question was just, I want to know at this point in time, how is Kate traveling around? Well, the left-hand side answers that question. But if later someone came along and said, well, actually, I want to know, where did Kate leave her car? I have no idea from the left-hand side. But from the right-hand side, I can make a reasonable guess. So I was on foot, and then I got in a car, and then I got on a train. So there's a reasonable chance that I left my car at the train station. And what about if I said that actually I lost my credit card and somebody has used it? A transaction appears on my account. How does my bank know that it wasn't me? If you look at the left-hand side, they might check my current location, and maybe it's on a train, so I can't be at the train station. But what if the state changed before they had a chance to check it? Whereas with the event-driven side, actually, I can work out, well, if I know at what point this event came through, because it should have a timestamp, then I can see at what point I changed from being in my car to on the train, and I can work out, was it me who made that transaction at the train station? So by shifting your viewpoint and being event-centric instead of data-centric, you can actually gain a lot more insight into what's going on in your system, and you can gain extra value that you might not have thought about up front when you designed your architecture. So what does this look like in practice? Well, in practice, we have this event backbone at the center of our whole architecture. And in the simplest case, we just have microservices where one sends an event onto the event backbone, and then another microservice pulls off the event backbone. And this kind of system actually works well even if you have existing data and existing systems, because you can feed those event sources into your event backbone, whether that be sensor data or, say, clicks on a website. And actually, the people who developed Kafka linked in, that's how they started. They wanted to collect all of these clicks on their website. Or it could even be from a database itself. So later, I'll have an example of how you can get that data into your event backbone. Once it's in the event backbone, you can do additional analytics on this data to gain those new insights. You can also have an event archive. So a lot of the event backbones aren't really designed to store these events forever. They're persistent for a reasonable amount of time. But if you need to store events forever, you might want to put them in a more persistent store, and one that's designed to store data for a really long time. And then we finally have notifications. So notifications are, by nature, events. So it makes sense that they work well in this system. So this is the kind of overview, nice picture of your event backbone and all of the different things that you can plug into it. So at this point, I'm going to talk about messaging versus event streaming. Because I work at IBM, a lot of people have heard of IBM MQ, which is a message queuing system, and I always get the question of, how is Kafka and message queuing different? Or event streaming and message queuing. So let's look at it. Message queuing has these kind of characteristics. The things like MQ that are designed for message queuing have transient data persistence, so a message goes onto a queue, and then someone comes along, takes it off the queue, and it's not on the queue anymore. They're generally aimed at targeted, reliable delivery. So for example, MQ has stuff built in so that when that queue is on the system, it's all very secure and you're going to a very specific place. And they're generally used for more request reply. So it's, I'm saying, please do this thing, and then you're responding saying, yes, I've done that thing, or whatever the response is, as opposed to an event, which is, this thing happened, I just wanted to let you know. Event streaming has these highlight characteristics. So stream history is the big one. Because you have, in an event streaming system, you want to persist those stream of events. They're immutable, so once an event has happened, it's happened. You don't go back and change it. It's quite different to the message queuing. And event streaming systems are really, really good for scalable consumption, because we have this transient data persistence in a message queuing system that means once the event's been read, it's now gone. And this bit, particularly with the scalable consumption, can be seen if you really compare what's happening a little bit under the covers. So let's look at point-to-point versus publish-subscribe. So in point-to-point, you have a queue. So this is a queue. We have producers to the queue. They put messages on the end of the queue, and consumers come along and read messages off of the queue. And the key thing is that because the consumers are taking the messages off of the queue and then they're not on the queue anymore, if you run a set of consumers, like we have 3 here, between them, they get all of the messages. But one particular consumer can't see them all, because once someone's read it, it's gone. Whereas in a publish-subscribe type model, you have the producers, again, appending to the end, but because you have this subscription, the consumers can get a copy of every single event that's gone on that topic. So a topic is what we call the grouping of the events in event streaming. And you can see here you can still have consumers working together, but the key thing is it provides you with the scalable consumption. Okay, so now that we've level set on message queuing versus event streaming, I'm going to look at a more complex example, because my little diagram with the sources and things is nice, but it doesn't get down to the real problems you run into. So I'm going to use this example. So you can see there's a link here at the bottom to the cloud architecture. So at IBM, we have a team that have put together this example to show ways to do event-driven microservices. If you want to have a look, there's a whole bunch of data. It gives all the sort of backstory of the scenario I'm about to describe, and also has example code. So you can go have a look. But what I'm going to do today is talk through this example, and we'll look at how we can build it up and use 4 different patterns to make event-driven microservices easier. So this is the scenario. We have a manufacturing company and a shipping company. So if you imagine you've made an order online, say it has to be shipped around the world. For today, we will use chocolate, because I like chocolate, and I recently went to San Francisco, and they have really good chocolate there from Ghirardelli's. So let's say I've gone home, and I regretted not buying more chocolate. So I'm going to make an order online, and I need that to be shipped back to the UK, so it's waiting for me when I get home. And these 2 companies are separate companies, but they want to work together. So this is the flow that my chocolate will have to take to get to me. So it will be manufactured and then taken to the port. It's going to go on a ship across the world and then arrive in the UK and go through customs. And the system that we will end up with will look something like this, which looks kind of complex, so we'll build it up from scratch. So let's start with our microservices. So these are kind of split, one side and the other. So the ones on the left-hand side belong to the manufacturing company. The shipping company, sorry. And the orders one is the manufacturing company. So for the shipping company, they have a voyages microservice, which is where they handle sort of assigning ships to go on specific voyages. They have 2 microservices that are attached to IoT devices. So the fleet microservice is basically gathering data from all of the ships they have around the world. So it will be things like the location, what direction they're going, what speed they're going, that kind of thing. The containers microservice here is not a Docker container, it's a real-life shipping containers microservice. So basically they have sensors on all of their shipping containers that are on their ships and gathering lots of different information. And the one thing we know about chocolate is we don't want it to melt before it gets to me. If you've ever had the Ghirardelli's chocolate, it has a really nice imprint on it. So it would be a shame to ruin that. So we need to know the temperature to make sure that the chocolate doesn't melt. And of course, the location is handy, because if a shipping container goes overboard, then we might want to know about it. And then we have our orders microservice. So this is owned by the manufacturing company. So I've placed my order. We'll just gloss over the details of that for a sec. The first thing I would ever want to do is to say, well, when is my chocolate going to reach me? And we could have the orders microservice constantly ask the fleet and the containers microservice for the location, but that's quite a lot of overhead. And I don't know how much you know about shipping containers, but they don't move very fast. So you're not going to get very much useful information every time you ask for that data. And equally, you don't really want the fleet microservice and the containers microservice pinging updates to the orders microservice all the time, because it's just going to overwhelm it, and then I can't take more orders. So that's where the event backbone comes in. What we can do is the fleet microservice and the containers microservice can publish all of their events into the event backbone. The orders microservice can subscribe to these events, and then we're good. So now the orders microservice is getting updates every time there's new data from these two microservices, and that means when I come along and ask where is my order, the orders microservice can respond straight away to say this is the last known location of your orders, or this is how far away they are. Okay, so we've now introduced our event backbone and seen that we can get some extra use out of that. But a minute ago I skipped over how do the orders microservice and the voyages microservice talk to each other. So once I've placed an order, a ship has to be assigned to a voyage for my order. Now we could just put a big database, and then they can talk to each other through the database, they can put updates, but as hopefully you've been told a lot of times, if you're doing this, then you're not really doing microservices. So the first pattern is you need a database per service. This gives you the benefits of your services being loosely coupled. So instead of having to update the database every time either of the companies wants to change something in their app, they have their own databases and they can evolve their apps at different times. It also allows you to choose the right database for that job. So different services might need their database for different reasons. And there are many different kinds of databases out there, so you can pick the one that's optimized for what that service really needs. And it works really well with the do one thing and do it well sort of idea. There are some drawbacks, however. So transactions that are spanning the different services suddenly becomes difficult. So when I'm placing an order and I want to know, is my order going to arrive before I get back home? Or that's probably pushing it, but say I want my chocolate to arrive before Christmas, that would be a transaction that's spanning both the orders and the voyages. And also querying the fact these databases is separated is also difficult. So we'll look at how we can solve that. The final one, which is just something there's not necessarily a solution, but is something to consider, is you do then have to manage multiple databases. Okay, so we've got our two new databases, but how can we solve this problem of transactions spanning? So who here was in the talk before this talk that was about transactions? Okay, not that many people actually. So in the previous talk, it was focused around this. It was talking about sagas. So a saga is a way of creating this kind of distributed transaction, but that then works. And the way you do it is you have a set of local transactions, and then with events between. And when you create your idea of what a local transaction is, you have to create compensating actions. Now, you can do this without events. You can do it with one service that's kind of orchestrating and saying, like, you do this, and then now you do this. But I think it's a bit smoother if you use your event backbone. And for this system, we already needed an event backbone, so it makes sense. So I'm going to break this down to what this means in practice for our example. So a request for an order comes in. The order microservice gets the request, and it puts an event on the event backbone that says an order has been placed. And then it also creates an event, a database entry, that says, here's my order, and I'm going to put it in a state of pending. Then the voyages microservice will come along, consume the event, check to see if there is a voyage available that will get the chocolate there at the right time for the order. And if there is, it can say voyage assigned it will create a database entry for that, and then it can be consumed back into the orders microservice, and it updates the database to say assigned. So this is the golden path, and the sort of local transactions here were the orders microservice and the voyages microservice updating their database. But if something goes wrong, you need to do compensating actions. So in this example, if we assume the orders microservice gets the order is placed, adds to the database, and then it gets consumed. At this point, if the voyages microservice determines that it can't fulfill the order on a voyage that's available, it could create an event that says, oh, the voyages are full, not allowed. And then the orders microservice has to take some compensating action. And in this case, it could be that it just cancels my order and I get an email saying, sorry, we can't fulfill your order. So this is how you can use a Saga with an event backbone to allow you to do those kind of distributed transactions. So in our event backbone, this now means that the voyages microservice and the orders microservice will publish events into voyages and orders, and then they can happily consume from each other. So doing a Saga has some benefits. It enables data consistency across the services without having a distributed transaction. But the programming model is more complex. The system that I show here with the kind of event and the local transaction, it's more difficult for you to set up. And this example was quite a simple one. If you get more complex ones, they can be quite difficult. There are different systems out there that will help you, but it is a complexity that you're adding. But one of the big glaring problems is I said, oh yeah, you publish an event and then you update the database, but actually, in order for it to be reliable, you need an atomic update to both the database and publishing the event at the same time. Because you don't want you to have published the event, but the database isn't updated, and then the orders microservice has an incorrect state. Or the other way around, it creates in the database, but the event for some reason fails, and then the voyage never happens, and the microservice is left waiting for something that's not going to happen. So we have this problem that we need to solve the update of the database and publishing the event at the same time. So this was pattern 2. So pattern 3 helps with that, and that is event sourcing. So for event sourcing, you basically represent business objects as a series of events. So in this example, our business object is an order. So the series of events might be things like order 0 created, and then maybe it creates order 1, so that's another business object. Order 0 updated, order 2 created. Then if you want to get a view of the database and what the current state looks like, all you have to do is play back the events in order. So first you read order 0 created and you get an order 0 pending, then order 1, so 1 is pending, order 0 is updated to assigned maybe, and then order 2 is created. So with event sourcing and having the event backbone as the source of truth, you can now reliably publish events when the state changes. And the extra thing you get for free is you now have an audit log as well of all of the changes that have happened. So in our more complex system, we now have the voyages and the orders microservice basically producing an event and then consuming back from the event backbone, and then that's when they create the entry in the database. So at all times, the event backbone is the source of truth. Now, it does have some drawbacks. There is a learning curve for implementing this. But also, because we're now saying that actually the event backbone is the source of truth, you could argue we don't really need the database. But a series of events and an event store is actually really difficult to query. So often we want some mechanism to query the data. Say if the shipping company said, I want to know where all of my ships are right now, or I want to know what the state of all of my orders are from the manufacturing company, that's something that you will struggle to get straight from the event store. So that's where the final pattern I'm going to talk about today, which is CQRS, comes in. So this is Command Query Responsibility Segregation. And what this basically means is when you create your microservices, you have two models. So you have a write model and a read model. And then what happens is a request comes in to the write API. So in this case, we're dealing with orders, so a new order comes in. The microservice will write an event into the orders topic on the event backbone. Then the other microservice will read that data in and write it into the database. And when it writes it into the database here, it can do that in a bulk if it wants to. It could process lots of events and then write it in as bulk. But the key thing is that this database here that the read model is using will be a query like optimized database. So it will be read optimized, so it's very queryable. That's what I'm trying to say. So that means later, if somebody comes along and says, actually, I want to find out all about these orders, then the microservice can look in its database and just return the data really easily. So this gives you these benefits. So now queries are really performant, and you have improved separation of concerns. So you're not trying to make the event backbone be everything to everyone, and equally, you're not trying to do that with a database that's shared by everyone. You have good separation of who is in charge of what. There are some things to consider. So it does provide you with some increased complexity, or quite a bit of increased complexity, and you do have to deal with eventual consistency. So when you're moving to having events at the source of all your systems, you do have to shift the way that you're thinking a little bit. And thinking about, okay, well, if I write to my database, it might take a bit of time before reading gets me the same result. So you do have to build that into the way you're thinking about and creating these architectures. So we've now got to nearly the finished picture. So we have our Voyages microservice and our Orders microservice. They're publishing events. They've also got their own databases. And then we've got the Fleet and Containers one also getting involved. So now what I'm going to do is talk about Kafka and how I think that can help you and why you should make Kafka your event backbone going forwards. And if you've already made the decision, hopefully this is things you can use going forwards. So at the beginning I said that we were looking at message queuing versus event streaming. And hopefully you can see, because the way we've built up our architecture in the previous one, we've got lots of different systems that are connecting into our event backbone. So having a stream history is important. All of the events that I was talking about were statements of things that have happened. So they're definitely events, not messages. They should be immutable. And we've got lots of consumers. So this was quite a simple example. When you scale out, you'll have lots more. So we really want something that fulfills all of these characteristics. And luckily, Apache Kafka does that. So for those of you who haven't heard of Kafka, it's an open source distributed streaming platform. And as promised, it's publish subscribe to a stream of events. You can store events in a durable way, and you can process streams of events as they occur. So let's have a little look at what is in Kafka that can help you on your event-driven journey. So Kafka is a distributed system. So you've got 3 or more brokers separated out. So these are individual servers where you would send your events. And one of the key things to know about Kafka is you don't just have topics, but you also have partitions. So for a particular topic where I'm sending my events, it gets partitioned and separated over the different brokers. I'm not going to go into it today, but there are built-in things within Kafka to have good availability so that if one of your brokers goes down, you can continue talking to the others. It does replication, but I'm not going to go into that. I do have a talk tomorrow if you are interested. But this partitioning, we'll see, will come in useful. So the first thing I want to talk about that can help you is around data replication. So although many people get told, don't just split all your apps up and then leave your database as one big database, often actually making the leap to breaking up your database can be a little bit tricky. And so Kafka actually has some things that might help you along the way. And the first thing is something called compaction. So normally when you send events into Kafka, you send all of your events and you would assume that they stay there for as long as you've told Kafka to retain them so that all of your consumers can read those events as they appear. But if you're trying to represent entries from a database in Kafka, you can use something called compaction, and this could help you move towards starting to have your other microservices pointing at the event backbone rather than one big database. So the way compaction works is in Kafka, we have these topics that are separated into different partitions. And each event in Kafka is a key and value pair. And basically, if you set your topic up and turn on compaction, so it's a switch you have to turn on in Kafka, it will periodically compact the topic and basically eliminate any duplicate keys. So what this means in this scenario, I've got keys A, B, and C, and then values A1, B1, A2, C1, C2. When the compaction happens, you'll see that any of the duplicate keys go missing. So, for example, for key B, I only had one entry. I swear I updated this slide. So it should say B1 down there. I think it says, oh no, it does say B1. I didn't update the next slide. Damn it. I can see the preview. So B1 there, it's going to change on the next slide because I didn't update the one after it. And then for key C, we have two different events, so it's the last one that came through. So it keeps C2, and then for key A, it's A2. And basically what this means is you can represent the rows in your database. So if someone did an update to a value, you could say, here's the new value, key, which is the ID for that field, and then you basically get a nice compacted set of data on your event backbone. So you can kind of use Kafka to help you start pointing more microservices at your event backbone, and initially they could just be taking these events and just copying them into their database. And Kafka also has something to help you copy things from databases to Kafka, and that's called change data capture. So Kafka Connect is something that comes as part of Kafka. It's basically a framework to help you connect other things to Kafka. And lots of people in the community have been writing connectors that will run on Kafka Connect, and quite a few of these use change data capture. So what you can basically do is, from your database, you can have an application running that will read the changelog into Kafka Connect. And Debezium is an open source example of things that do this. So Debezium have connectors for quite a lot of different databases that all do CDC. They then send those events into Kafka, and then you can have a microservice that pulls all the events from Kafka and then puts them back into their own database. So between the compaction and change data capture with Kafka Connect, Kafka provides a few different ways that you can start to try and segment or like break apart your databases and not have one big database that everyone's using. Okay, so let's talk about event sourcing. So this is where the partitioning comes in really handy. So for event sourcing, you are representing each of your business objects as a series of events, and the order here matters. So you don't want to have an order being updated before it's being created, because that wouldn't make any sense. But with a lot of event streaming and event-driven systems, you will have a lot of data flowing through, and so you want to be able to scale to consume it. Well, Kafka allows you to connect your consumers in a way that's called with consumer groups. The other thing that Kafka will do is help with this ordering. So when my producers produce events, what Kafka will do is every event that has the same key, it will put it in the same partition. So you can see here on my partitions, I've got orders 1, 5, and 7 in the top one, 2 and 4 in the middle one, and then 3 and 6 in the bottom one. And that's not accidentally, because I have put the same key for, so like order 1 will always have key 1, Kafka will put it in the same partition. Then when you connect your consumers, you define them as part of a group. And it's really easy to do. Basically, you start up your consumer and you have to provide a group ID to connect, and you just all pick the same one. So here, consumer group A have picked the same ID, and then consumer group B have picked the same ID. And you'll see that what Kafka will do is basically route the events so that between all of the consumers, they will see every event. But it means you can scale up to have as many consumers as you have partitions. And ordering in Kafka is guaranteed per partition. So because we've, in our producers, put the key, they've then, for example, on the top row, order 1 has ended up in partition 1. The order is guaranteed because they're all in the same partition, and then when my consumers connect, if they work as part of the same consumer group, only one consumer will get access to that data. And if I actually added an extra consumer, it wouldn't get any data because I don't have any partitions left. You can have one consumer from a group reading from more than one partition, so that's useful as well. But the key message here is that by using your keys and using your consumer groups, you can actually do event sourcing at scale. Cool. So the final thing I'm going to talk about is Kafka Streams, and this will allow us to add even more insights into our existing architecture. So Kafka Streams is another, well, it's not a framework, it's more of an API really, but it's built into Kafka. And basically what it allows you to do is do stream processing in a really easy way with Java. So I've got some Java code here, which is using the Streams API. So you can see that I've got builder.stream from my input, so that's my input topic. I'm filtering, so I'm filtering out all of the keys that equal bingo. I'm then mapping them and saying that I want to take the key value pair and convert it to key, but uppercase the value, and then put it to my output topic. And what this will then do is, on my output topic, I'll end up with these two, because the ones in the top that had bingo were green and blue, and then I uppercase them. So what Kafka Streams allows you to do is to do all of this stream processing, but you're doing the processing in the app. You're not having to have a separate processing engine running somewhere else. And so in our event-driven system, this allows us to add a little piece. So we could have the orders microservice talking directly to the ships and the containers. But actually, the orders microservice probably doesn't care what temperature my chocolate is at. So instead, it would make more sense if we have a streaming app that's streaming from these and putting a new topic, which is order update for the location. Then my orders microservice has less data that it has to churn through. And from here, we can then add even more value if we wanted. So if I wanted to know every time the temperature got over a certain value, I could have another topic and another streaming app that's getting that data. So you can see once you've moved to being event-driven and having this event backbone at the center, not only does it help you in building microservices and getting them to communicate effectively, but you're suddenly getting all of this extra insight and extra data that you weren't really seeing before. And you can answer questions that you hadn't even thought of when you built the system. So this is our final picture, which is the one I showed earlier. And if you want to go and get started with all of this event-driven stuff, you could run an event storming workshop. So I've got a handy link here if you want to know about that, because the biggest thing first is kind of shifting your mindset. So this can be a really nice way to start thinking in an event-driven sort of way. The slides will be shared, so you're okay. Make sure to think about those patterns, because they are useful and they will help you to solve problems as you go through. And if you are interested in learning more things about Apache Kafka, I am doing a bite-sized talk tomorrow. I won't be repeating any of the things really that I talked about today. I'll be talking more about how to get started in the kind of core of how Kafka works and replication, that kind of thing. So yeah, there's some handy links here to the different Kafka docs, to Debezium, and then the website I talked about earlier. Thank you very much. If anyone has any questions, we have 4 minutes and 53 seconds. Yep, I think there's a microphone.
Do you have any data using Debezium for database?
Do I have any?
Data, the cost of Debezium for database.
What do you mean the cost?
When we use Debezium,
Yeah.
The cost of performance, like
How on what the database?
when data replication, when using Debezium.
So I don't have any particular figures, but the way Debezium works is it basically reads the change log of your database, and I know various people who use it and haven't had any particular complaints.
Okay.
If you have some more specific questions, so I personally don't develop Debezium, but I do know the person who is in charge of the project, so I can definitely connect you with him if you have more questions on that one.
Thank you.
It does support a lot of different databases, though. And actually, I didn't link it here, but if you go to About Event Streams, we actually have a connector catalog where we link lots of different connectors, and all the Debezium ones are on there. So if you wanted more links to docs, then you can get those there as well. Any more questions? Feel free to come and ask me after or in my talk tomorrow. Thank you.